Alright, good morning everyone. My name is Mohammed and I'm here to introduce Arush Kandakuri. Arush entered at Stanford University's Alexander Lab under the mentorship of leading researchers, where he worked on developing innovative methods for solving amyloid fibrosis and contributed to advancements in amyloid transthyretin cardiomyopathy research. Please join me in welcoming Arush.
Alrighty, thank you, Mohammed, for that wonderful introduction. So, for those of you who don't know me, I'm Rouge. This summer I interned at Stanford's Cardiovascular Institute, and I studied Fibroquant, which is an image-based color thresholding to differentiate amyloid transthyretin from healthy controls via fibrosis signal analysis. To start off, amyloid transthyretin is a disease in which amyloid proteins accumulate within the heart. It leads to stiffness and can even cause death through heart failure. We see that this is common between people over 80 years old, with over 10 to 25% of people having this condition. It's rare and progressive, with no cure currently found to it. So what we do with Fibroquant is we aim to provide a streamlined way to quantify the amount of fibrosis within the sample. So just to kind of give you a gist on how a patient's heart tissue looks like under ATTR, a healthy heart tissue would have a lot of red blood cells. So this would be a lot of heart tissue, and we see that there's not a lot of white area in this, especially in this region. On the other hand, with the ATTR sample, there's a lot of white, which would indicate that there was in fact healthy heart tissue there at some point, but now it's not there, which is why there's white or gray area. The goal with our research is to use Fibroquant to differentiate the heart tissue as samples as amyloid transthyretin or healthy control based on the percent of fibrosis in the sample. So with our experiment, we hypothesized that Fibroquant will be able to successfully differentiate between amyloid transthyretin and healthy control based off our analysis. So just to start off, when we're doing our experimentation, all the data analysis, which is me, I'm unaware of which mice are ATTR and which mice are controlled, to make sure that it's kind of completely blinded and adds a level of security to the experiment. To start off, we import the 10x and 20x microscope images into ImageJ or Fiji. So the images, I'll explain a little bit later, but the microscope images are taken from basically from the heart tissue samples of mice that I'll get to a little bit later. What we do is we do the image, adjust, and color thresholds to set custom thresholds for either blue or red and blue, which I'll talk about a little bit later, to get those specific values. So to get just the blue, which would be the fibrosis, this is the bad stuff that we don't want to see in a heart. What we do is we set the hue to 171 to 187, the saturation from 0 to 255, and the brightness to 0 to 225. These two values would stay the same between blue and red. The only value that changes is the hue to get blue or blue and red. So this would capture the blue signal area, which would be the fibrosis within the sample. So once we get that blue signal area within the image, what we do is we select it and we measure the amount of it and we record that within our spreadsheet. After that, we then move on to blue and red signal analysis. What we do with that is we just change the hue from 151 to 189 to get the whole blue and red signal analysis. The red would represent the healthy heart tissue and the blue would represent fibrosis. So we see the blue over the blue and red, which would be the healthy heart tissue. So once we do that, we divide it and we can get the total signal area of the fibrosis in the sample. Just to kind of run you through the process of what the image looks like during the ImageJ analysis, we start off with the full image. This is just what it would look like originally. And this is a pretty extreme patient. So we pretty much see more blue and more fibrosis than we actually do healthy heart tissue. And that's pretty bad. So this is not actually one of the mice, this is from a patient that we saw within the clinic. So once we take this sample, we then set the threshold color hues from 171 to 187, and we see a lot of red being highlighted there, and purple. Please disregard that. What ImageJ does is it can pick up on the blue within the image and be able to categorize that as the fibrosis. So it would select and measure the pixel area, and we would get that blue fibrosis. After that, we move on to the blue and red by changing the threshold color hue from 151 to 189 to get the blue and red fibrosis and healthy hard tissue. And we'd measure that area. Once we get that, we have the blue and red signal area in order to find that the total fibrosis within the sample, for this one at least, was pretty extreme. It was 68.3%. So we saw that because there was so much fibrosis, we saw that there was such a high percentage of fibrosis recorded by the imaging. And we used 100 female mice samples and 200 male samples. So this would mean 5 female mice and 10 male mice. And once again, I was unaware of which mice were ATTR or controlled. So just to kind of summarize the whole process, what we do is we start off by taking a mice. Sorry if the text is kind of unclear, but we take the mice and then we kill it in a humane way. And we take that heart tissue from the mice, we splice it into a bunch of different samples to be able to put it under a microscope. After that, once we put it under the microscope, we take 10 images, 10 of which are 10x, and another 10 are 20x from that sample. So that's what led us to 300. Once we get that, we use the image Fibroquant tool, which is the ImageJ tool that I talked about, to run the analysis, and then we run a statistical analysis from that data. After that, we can get the results, which I'll get into just now. So here are the outcomes. We see that most of the data is between 0 to 3% or 4%, with some outliers nearing 10 or even 15%. And we see that the average for the data is around 1.237%. So starting with male ATTR mice, we see that male ATTR mice in fact do not result in a significantly higher signal area compared to the healthy control. So we see that the p-value in both scenarios, the 10x mice and the 20x mice, in fact show a p-value greater than 0.05%, which means we can't conclude that male ATTR mice would lead to a difference in fibrosis. On the other hand, female ATTR mice in fact do result in a significantly higher signal area. And we see this especially with the 10x female mice and the 20x mice, but especially with the 10x mice. The reason we believe that there's a significantly higher p-value or lower p-value for the 10x mice compared to the 20x mice is because we believe there's some sort of sampling bias when selecting the portion of the sample that we use as part of the imaging. So that just kind of leads to a little bit of bias because we choose the values or the area within the sample that has a lot of fibrosis to kind of yield better results, and that's common within the science. So in 10x image, for the 10x images, we have a p-value of less than 0.01 and a p-value of 0.05 for 20x female. So looking at the differences in gender, we saw that the p-value is greater than 0.05 for the 10x male and female, comparing the male and female ATTR mice. So, and this is actually a good thing because we want to make sure that it's constant and that the difference in fibrosis is not a result of gender. So we see that it's pretty much the same, so we can kind of just keep that as a constant variable. Looking at all the ATTR mice overall, to kind of conclude, we see that the combined ATTR mice for the healthy control for the 10x and 20x both show a strong p-value of less than 0.01, and that means that we believe that our Fibroquant imaging really does work and can kind of differentiate, regardless, especially with the female mice, the amount of fibrosis and differentiate how much fibrosis is within the heart cell. So to conclude, the male mice did not show a significant difference in ATTRs in the ATTR samples, while the female mice did in fact show a significant difference. And we saw that the hypothesis was in fact correct, that Fibroquant is in fact able to differentiate between amyloid transthyretin and the healthy control samples based off the fibrosis signal area. Here are my references. Thank you. Yeah, so that's a good question. Within MHA, those are the kind of thresholds that they give us, and the professor gave us as being red or red and blue. So, threshold that I gave for red. Yeah, the threshold that I gave for red, 171 or 187, or sorry, blue. This would encompass just the blue signal area, while the threshold for blue and red, that would encompass blue and red. That would give 151 to 189, so that would kind of encompass both. Yeah, pretty much. Yeah.
Another question. For the female mice, you said it was more statistically significant.
Yeah.
Could you please repeat like why that might be so?
Yeah, so it's because of the p-value, pretty much.
No, like you said, there were twice as many like female. Like you said, like the way you sample the mice and females will different from males.
No.
Is it the same?
Yes. Yep.
Could you go to the like red and blue slide? Yeah, I was just curious because you said like the fibers like on top were all like fibrosis, meaning that they were like bad, right? So how did it differentiate between like red and blue and like also purple?
Okay. So are you talking about how kind of? I think this
Yeah, it
is
sounds
a
like
better image.
Yeah, like what's the difference between like blue, red, and blue?
Blue, you mean like, are you talking about how just blue and then blue and red combined?
Yeah.
So blue, so you can't see it with the naked eye, but ImageJ will pick it up. The blue is the subtle pixels that you can see, or you can't really see within the image, and the blue and red would be the within the image, basically like the pixels, the RGB value between the hue of 151 to 189, get blue and red.
I just felt like what's the difference between like what's the difference in the fibrosis like that you're picking up on?
Difference.
Like is a red versus blue and red two different types of fibrosis? Like
No, it's not.
so yeah, I'm just asking like what's other than the two different colors, like what's the difference in that part of your methods?
Yeah, so the blue would represent just fibrosis. And then blue and red would represent the fibrosis with the healthy hard tissue. So we can see the percentage of the sample that has the fibrosis. Yeah.
Can you go back to the slide with the like 10x versus 7x?
Could you repeat that?
Can you go back to the slide with like the 10x versus 20x results?
Yeah.
Wait, 10x and 20x was for like how zoomed in it.
Yeah.
So why is there like different like percent fibrosis area depending on how much you zoomed in the image? Like shouldn't it be the same as the same images, just zoom in?
So they're different images, first of all, and that's a result of sampling variation.
Okay.
Yeah.
I think going off of what Karthik said is that, like, I understand why you concluded that, it's not significant higher in male mice and vice versa with female mice, but do you know specific reason why that is so?
Yeah, so generally, so kind of just a run back, what our tool kind of eliminates is the polarizer lens within a microscope. So that's, it's a cost to a lab to have a polarizing lens within the microscope. So what this does is basically eliminates the need for that. So kind of going back to your question, what it does is essentially minimize the need for that polarized lens.
Is there a specific reason, like, what I'm asking is, can you, like, it's fine if you don't, because obviously, it's another question, but regarding to, like, is there a specific reason why female mice will have that significantly higher signal here compared to male mice, which they don't?
That we don't know for sure yet, but right now within humans, it's more common within male mice. So the female mice, this can kind of be more applicable to female patients who might have the disease. Yeah.
Since cystic fibrosis mainly affects the lungs, is there a reason why you chose heart samples?
This is in no way related to cystic fibrosis.
Oh, I thought it was.
So the fibrosis is just the amyloid deposit, like as a result of just the amyloid deposits. that wreak havoc within the heart tissue. Yeah. It's in no way related to like the lungs in any way. Yeah.
What statistical test did you run against your p-value?
Pair T test. Yeah.
You said earlier that you needed to fill the mice amount you made weight something about.
Yeah, so the way, I didn't actually do it, but it was one of the lab people. What they do is they take the lab and they put it inside a chamber, and they close the chamber, and in the way that the mice are killed, it's actually, they wouldn't feel any pain, so it's kind of, we have to comply with those standards to make sure the mice are okay.
I was just wondering why you did this.
Could you repeat that?
Like, wasn't necessary for this, like, you need to kill them or kill them?
Yeah, if we're gonna take the heart out, we kind of do need to kill it. Yeah?
Could the female mice have a lower p-value due to like a smaller data size compared to the male mice? Because you had 200 male and only 100 female.
Yeah, that is a topic of concern. But going back to it, it's just so significant that we don't think that the variation in the sample is making that much of a difference. Yeah?
Why did you choose to sample double the amount of female mice?
That's just the mice that we had available. Yeah?
Did you think of like, what do you think about like why those female mice specifically have higher values? I don't know if p-value itself, I think like the underlying reason.
I'm not actually sure, but I'll get back to you. Yeah?
I'm still confused why did you decide to use two separate images for the 10 and 20? Why wouldn't you just use the same image on 10 and then use it again on 20 to compare the difference between 10 and 20?
So the sample that we take the 10x and 20x images are the same at the end of the day. But the variation between 10x and 20x, we did that because we just wanted to see if kind of having a more clarity within the image would result in more fibrosis or less fibrosis. So that's just kind of what we did. Yeah?
How do you take this into account?
Yeah, so I definitely reached out to a lot of people, personal connections, and definitely it definitely probably helped that I had previous internship experience as well to kind of blend there as my email. Yeah?
Did you do it in person at Stanford or was it online?
So 3 weeks of it was in person, and then 6 weeks of it was online. Yeah?
Why did you take the area of the blue red sample instead of just like the total pixel area?
Yeah, that's a good question. So the reason we did that is because there's a lot of other gray area or a lot of just a lot of stuff that we don't want to include within the analysis, like potential nuclei that's just like wastage or any wastage within the heart tissue. So we just don't want to include that as part of the sample. Anybody else? Okay, thank you guys.